how are you? How is the study going? I'll explain to you today the dynamic equilibrium. In equilibrium, there are two things happening at the same time, two different reactions. One is backward, one is forward. They are happening at the same time in opposite direction, and they are happening at the same speed and rate. So there are two kinds of changes here. The first one is changes that you cannot see and the changes that you can see. So as the name microscope says things that we don't see, we are also going to say microscopic changes. While the macroscopic changes is the things that I can see with my naked eye or even measure. So a change in concentration, a change in pressure, a change in temperature are things that I can measure and see. While chemical actions happens, binding of molecules or breaking down of compounds, I cannot see that, so it's microscopic. In the equilibrium, the microscopic changes keeps happening. So the nitrogen keeps reacting with the hydrogen to form the ammonia, and the ammonia keeps reacting with the ammonia keeps breaking down into hydrogen and nitrogen. So these are microscopic changes that keeps on going. What about the macroscopic changes? This is the things that stops. So if you check the concentration at equilibrium at any time, or you change colors or pressure, you'll say it is fixed, so it doesn't change. So although that I can see that the equilibrium has no change in microscopic properties, but the microscopic changes are happening, although I cannot see them. That's what we call the dynamic equilibrium. So the equilibrium here is dynamic. It's not static. It's not something that doesn't change. The static equilibrium is a kind of equilibrium that happens due to no changes. So if two people are sitting on the seesaw and trying to play, and one of them is sitting here and the other is also just sitting here, this is a kind of equilibrium. But this equilibrium is static because it's not only that I don't see any changes, they are actually making no changes. So there is no changes either macroscopically or microscopically. One of the conditions of equilibrium is that it should happen in a closed system. A closed system is a system that does not allow any matter to come out of it. You have a closed bottle or a closed container, flask or test tube or whatever system closed and no matter can come outside of it, that's called a closed system. Even if the heat can come out of it and it's not insulated, still it's called closed system. If any matter can come out of the system due to an opening in it, then I'm gonna call it an open system. One of the conditions for the equilibrium to happen is that there should be no opening. The system has to be closed, and in this case I will say that there is equilibrium. But what if I have two things or two reactions happening at the same time and in opposite directions, but the system is open? I will not call it equilibrium, I will call it a steady state system. So the steady state system looks exactly like equilibrium, the only difference is the open system instead of closed. There is one proof that this equilibrium is not always the state in the reversible reaction. Do you remember us saying that the reversible reaction doesn't mean that necessarily there is an equilibrium? One proof of that is that when you start the reaction, so if you started the reaction between nitrogen and hydrogen, at the beginning there is no ammonia formed yet. So since there is no ammonia formed, because this is still time 0, This is still initially, so there is no backward direction. How come there will be forward and backward directions in equilibrium if you still don't have a backward direction? You don't have a backward direction because the products are still zero. You just did not start the action. You did not just mix the reactants together. So after some time, the nitrogen and hydrogen starts react to form a small amount of the product. That's the NH3. And once this is available, then you can talk about the backward reaction. Even when this happens, there is not still too much backward reaction to be equal to the rate. So still this one is still much faster. After some time, the ammonia breaking down into NH3 and N2 will go to have some more speed, and finally you reach the point at which the two speeds or the two rates are equal. This is what you call equilibrium. So when you start the chemical reaction, if you want to draw this in the form of a graph, so the graph will tell you that this is the x-axis and this is the y-axis. In the x-axis you have the time, so how much time has passed since the reaction has started, and here you have the concentration of the reactants and products. So let's see, you started with a certain amount of reactants, like let's say you have a reaction between 3 moles of A and 1 mole of B to form 2 moles of C. At the beginning, the A is a high concentration, so it starts decreasing by time, and after some time we will find that this is going to a steady graph. So the graph is going to flatten here. Let's draw it again, maybe better this time. So this is the graph. It looks a little bit better now. This is the A. What is the A? The concentration of A is what we can write it in the form of brackets. So when you want to talk about the concentration of A, we talk about A between square brackets. What about B? The B also starts in a high concentration and then slowly goes down and flattens. Here I can see this a little bit circular. I don't want it to be circular, so I'll just draw it by hand. I'll just draw it by hand like that so that it flattens, but I don't want it to be circular even if it's not that good. Then the concentration of B is what we write as B in between square brackets. What happens to the products? The products start in a different way. The products at the beginning is 0, and then slowly it will start to increase. Then after some time it's going to flatten. If you see that at certain point the rate of the reactions will start to be the same. At this point I will see that they all flattened and they will all have the same rate. They will all have the same rate. You cannot say they have the same concentration, but you can say that their concentrations become fixed as we agreed in the previous part. So in this part there is equilibrium because the rate of changing of C and the rate of changing of B and the rate changing of A is the same. This is where the equilibrium happened. I can say that the concentration of A, which is A between brackets, decreased. I can see also that the temperature of the system might increase and the number of effective collisions was 0, and we'll explain this in details. But all we want to know now is that the concentration of A decreased while the concentration of B also decreased, but the concentration of C has increased. Since we draw these two curves in black, we can change it into black here also. So let's just write this all in black, and this is black. If you want, you can make this separate as blue, so it will always be blue here, and it will be blue here, and also blue here. Hey, I want to tell you to remember that we always have fast versions from these videos. So these videos will be only suitable if you are still studying slowly in the middle of the year. But if you are coming here to revise equilibrium and want something fast, you will find special videos for the revision. These are usually shorter, faster speed, and more condensed and crammed content.